In Changsha, China, on a flat, empty lot in the kind of in-between urban district that could be anything or nothing, something happened in February of 2026 that most people in the construction industry spent the next several weeks insisting couldn't be real. As night fell, trucks began lining up like a convoy. Steel modules, already wrapped in insulation and glass, already fitted with plumbing and wiring and ventilation ducts, slid off trailers with the ease of enormous freight containers. Cranes moved in. Crews in hard hats worked with the calm efficiency of people who had rehearsed this exact choreography dozens of times before. By morning, a skeleton had become a shape. By the next day, 28 hours and 45 minutes after the first module touched the ground, that shape was a complete 10-story residential building. Not a framework, not a shell, a building with functioning floors, embedded wiring, running water, and walls already in place, built by a company called Broad Group using a structural material called B-core steel that is, according to every independent test conducted on it, approximately 10 times lighter than conventional concrete and, depending on the load case being measured, somewhere in the range of 100 times stronger. When videos of the build began circulating, sped-up footage of the entire structure appearing to grow out of the ground overnight like a time-lapse of a plant pushing through soil. The comment sections of every engineering forum that picked it up ran the same pattern. People insisting it had to be staged, then people posting the original South China Morning Post documentation, then engineers who had actually reviewed the structural specifications, spending 3 paragraphs explaining why the numbers were real and why that made the situation considerably more significant than a viral video suggested. The numbers are real, and the situation is considerably more significant than a viral video suggests. Here is the problem that this story is actually about. Because the 10-story building in a day is the most visually striking piece of it, but not the most consequential. The most consequential piece is what sits underneath it. A country that produces more than half of the world's cement and consumes more concrete than the rest of the world. Combined, has spent the last decade systematically engineering its way out of concrete dependency. Not because it ran out of concrete, but because it understood before most of the world did exactly how catastrophic the carbon math of concrete actually is, and how completely the country that solves that math first will reshape an industry worth trillions of dollars and touch more of the physical world than almost any other material humans have ever produced. By the time this is over, you are going to understand exactly what China has built, why 2 separate breakthroughs happening simultaneously are more significant together than either one is alone, and why the world's biggest cement companies have, according to their own executives, begun describing both developments as a matter of survival rather than a matter of competition. If you've ever thought of concrete as the most boring subject you could possibly spend time on, stick with me, because I genuinely believe that by the end of this, you're going to think of it as one of the most important stories in the world right now. Let's start with the problem, because the scale of it is something most people have never been told directly. Concrete is the most consumed substance on Earth after water. Every single year, humanity pours roughly 26 gigatons of concrete into the ground. That's 26 billion metric tons, a number so large that it's essentially impossible to picture, so try this instead. It's roughly 3.5 tons of concrete for every single person alive on Earth, every single year. Bridges, dams, roads, apartment buildings, offices, tunnels, ports. The entire built environment of modern civilization is, at its foundation, concrete. It has been for more than a century, and the projected demand curve doesn't flatten. Global cement production is expected to increase by 50% by 2050, as billions of people in the developing world urbanize and build the infrastructure that wealthy countries built in the 20th century. And here's the problem embedded in all of that, the one the construction industry has known about for decades and largely failed to solve. Cement production, the process that makes concrete work, is responsible for approximately 8% of all the carbon dioxide humanity releases into the atmosphere every year. 8%. To put that in context, all commercial aviation globally accounts for roughly 2.5% of annual CO2 emissions. The entire global airline industry, every flight on every aircraft, on every route in the world, produces less than 1/3 of the carbon footprint of making concrete. If the cement industry were a country, it would be the 3rd or 4th largest emitter of CO2 on Earth, behind only the United States and China. Global cement manufacturing released 1.6 billion metric tons of CO2 in 2022 alone, and on the current trajectory, that figure is projected to reach 3.8 billion tons per year by 2050. The reason the carbon footprint is so difficult to eliminate is structural. It isn't just that cement factories burn a lot of fuel, though they do. It's that the chemical process of making cement clinker, the core reactive ingredient in concrete, involves heating limestone to approximately 1,450 degrees Celsius. And the heating itself causes the limestone to chemically decompose and release the CO2 that had been locked inside it for geological timescales. Nearly 60% of cement's carbon emissions come not from the fuel burned, but from the chemistry itself, which means you can't fix it just by switching to renewable energy. You have to either change the chemistry or use dramatically less cement, and for over a century, nobody found a reliable way to do either at industrial scale without sacrificing the properties that make concrete the material it is. That is the problem China just cracked. Twice. Using two entirely different approaches. And the fact that both happened in roughly the same period, backed by the same underlying industrial policy logic, is not a coincidence. The first breakthrough is the one that got less visual attention, but is arguably the more fundamental of the two. In 2025, a team of Chinese researchers published findings describing a process that makes concrete over 80% stronger while cutting cement use by 40% without adding any new ingredients, no novel chemicals, no expensive additives, no exotic materials that would make the process economically impossible at scale. The key was pressure. Specifically, treating the concrete during a critical early phase of its curing process with precisely controlled pressurization that changes how the cement particles bond at the microscopic level, dramatically improving the density and strength of the final material while reducing the total amount of cement needed to achieve a given structural specification. Because strength and cement content are directly linked in conventional concrete, the more load a structure needs to carry, the more cement goes into the mix. A process that makes concrete 80% stronger with 40% less cement doesn't just cut carbon emissions proportionally. It fundamentally changes the economic and technical trade-offs that every structural engineer makes when they specify a concrete mix for a project. The implications are direct and significant. If you need less cement to achieve the same structural result, you pour less cement. Less cement means less limestone calcination. Less limestone calcination means dramatically less CO2 released as a product of the chemistry itself, the part of cement's carbon footprint that renewable energy can't touch. And because the process uses no new ingredients, the manufacturing infrastructure for it can be built on top of existing concrete production facilities rather than requiring the construction of entirely new plants. That matters enormously for commercial viability because the history of green construction materials is littered with technically elegant solutions that never scaled because they required someone to write a check for a completely new supply chain before a single unit could be sold. Engineers in Germany, Japan, South Korea, and the United Kingdom began pursuing licensing conversations shortly after the research was published. The reason for the speed of that interest is the market sitting behind it. Global cement production is a market worth hundreds of billions of dollars annually, and it sits inside a broader construction materials market worth trillions. Any process that credibly addresses both the structural and the carbon performance of concrete simultaneously without requiring a new supply chain is not competing in a niche. It is competing for a piece of every major infrastructure project on Earth. Now here is where the second breakthrough enters the picture, and where the two developments together start telling a story that's larger than either one alone. Broad Group has been building with B-Core Steel since 2009, when its founder, Zhang Yue, decided that the construction industry's fundamental problem wasn't material science, it was manufacturing philosophy. The premise of B-Core is straightforward in principle and extraordinary in its engineering. 2 layers of corrosion-resistant stainless steel enclosing a lattice of extremely thin capillary tubes bonded together by copper brazing. The result is a structural panel that is, by independent testing, up to 10 times lighter than conventional reinforced concrete of equivalent strength, with ductility and seismic resilience that exceeds traditional materials in both categories. Broad Group claims a lifespan for B-Core buildings 20 times longer than reinforced concrete equivalents, and a carbon emissions reduction of 80 to 90% compared to conventional construction when the full building life cycle is accounted for. The company has already demonstrated the system at scale that would have sounded like science fiction 15 years ago, a 57-story building completed in 19 days, and now a 10-story residential block in 28 hours and 45 minutes, documented, filmed, verified, and picked up by the South China Morning Post, Global Construction Review, and engineering publications around the world. The Changsha build in February 2026 was not a stunt. The modules that assembled the building had been manufactured over 3 months in a factory-controlled environment, the kind of precision manufacturing environment where quality control is genuinely possible, where every bolt hole is cut to tolerance, every wiring conduit pre-installed, every pipe run before the module ever reaches the site. The on-site operation was the last step, not the main event. 3 cranes, a large coordinated workforce, and 28 hours and 45 minutes later, the result was a building rated to withstand level 9 earthquakes and typhoon force winds. Structural performance that exceeds most conventional concrete construction, assembled with essentially zero site waste, no wet concrete, no formwork to build and strip, and a noise and disruption profile that, in the words of one account of the build, felt more like a quiet logistical operation than a construction site. The economic logic of this, once you work through it, is not subtle. Traditional construction on an urban lot in a major city carries financing costs for every month of construction time. It carries labor costs for on-site workers dealing with weather delays, safety incidents, and the inherent unpredictability of assembling a complex structure from raw materials in the open air. It carries waste disposal costs for the materials that don't fit, don't work, or get damaged. Modular prefabrication eliminates most of those variables by moving the complexity into the factory, where conditions are controlled and repeatable, and making the on-site operation as simple and fast as possible. Broad Group claims that modular construction of this type reduces overall project costs by 30 to 50% compared to conventional methods. Even if the real number is half that, it is a competitive advantage that conventional construction cannot easily replicate, because the underlying cost structure of on-site concrete work is difficult to compress regardless of how much you optimize it. China's prefabricated building exports tell the story of where this technology is actually heading. According to China's General Administration of Customs, prefabricated building exports rose from $1.47 billion in 2015 to approximately $4.34 billion in 2025. In the first quarter of 2026 alone, the figure grew by 45% year on year. The major destinations, the United States, Indonesia, Malaysia, Russia, and Australia, precisely the countries facing the combination of soaring construction labor costs, acute housing supply shortages, and lengthy conventional building timelines that make faster, cheaper prefabricated alternatives most attractive. A Chinese national in Perth, Australia, had a 70 square meter prefabricated home from China, including bedroom, living room, kitchen, bathroom, windows, and lights, installed for approximately 12,500 Australian dollars. Local builders quoted her more than $100,000 for the same result, with a 6-month wait before work could even begin. The Chinese government has not been a passive observer of any of this. In 2025, Chinese authorities issued a national directive explicitly promoting prefabricated and smart construction methods, establishing long-term support mechanisms for green and low-carbon construction transformation, and directing city and district governments to adopt new industrialized building systems as part of China's 15th five-year plan targets. Shanghai released a dedicated action plan with financial support for qualifying prefabricated projects. Beijing, Guangdong, and Shaanxi followed with their own regional frameworks. When Broad Group shipped modular components to the United Arab Emirates in October 2025, customs authorities in Yueyang City tailored a full process clearance plan that cut processing time by more than 10 days and reduced logistics costs by around 3,000 yuan per shipment. That level of state infrastructure support is not accidental. It is the same industrial policy logic that produced CATL's battery dominance and Huawei's telecommunications equipment scale. Identify the technology, support it comprehensively, get to market first, and establish the standards before competitors in other countries have finished debating whether the technology is real. Here is what that means for the rest of the world's construction industry, and why the executives of the world's largest cement companies are correct to be paying close attention. The global cement market is dominated by a small number of very large companies: Lafarge-Holcim in Switzerland, CNBM in China, Heidelberg Materials in Germany, Cemex in Mexico, that together control a significant portion of global production capacity. These companies have spent decades building the kind of infrastructure that is, by its nature, extremely capital intensive and extremely slow to depreciate. Quarries, kilns, grinding mills, distribution networks. The fundamental business model of the cement industry is built on the assumption that concrete's position as the dominant structural material for large-scale construction is essentially permanent, because the alternatives are either too expensive, too structurally limited, or too unfamiliar to building codes and engineering specifications to gain meaningful market share. That assumption is what both of China's breakthroughs are simultaneously attacking, one by making concrete itself radically better and cheaper to produce with less cement, which may cannibalize volume even as it defends the material's relevance, and one by offering a viable, demonstrated, commercially scaling alternative that replaces concrete as the primary structural material entirely in the buildings where it's deployed. Neither development, on its own timetable, eliminates concrete from the global construction industry. Concrete is embedded too deeply in building codes, engineering education, contractor experience, and the physical infrastructure of material supply chains to be displaced rapidly, even by a technically superior alternative. But the combination of the two, plus the Chinese government's explicit policy commitment to scaling both, plus the export growth trajectory, plus the housing affordability crisis in nearly every developed market that is actively creating demand for exactly the kind of faster, cheaper building approach that modular prefabricated steel enables, is a pressure that the conventional concrete and cement industry has never faced in this form before. It has faced environmental regulation. It has faced energy cost pressure. It has faced competition from steel and timber in specific building types. It has not previously faced a competitor that is simultaneously cheaper, faster, structurally superior in several measured categories, and backed by the industrial policy infrastructure of the country that already produces more than half the world's cement. The question worth sitting with is one that most people in the construction industry are still processing in real time. When China built that 10-story building in 28 hours in Changsha, the reaction in engineering forums was almost uniformly the same. Initial disbelief, followed by people going to find the source documentation, followed by engineers spending significant time working through the structural specifications. And what the documents show is that the performance claims hold up. B-core panels have been independently tested. The seismic ratings are real. The weight-to-strength ratios are real. The carbon reduction numbers are real. The building that appeared in Changsha overnight is standing, occupied, and rated for conditions that most conventional concrete structures in the same region would not comfortably meet. That shift from "this can't be real" to "this is real," and I need to figure out what it means for my industry, is the moment this story actually begins. Not for Broad Group, which has been building this technology since 2009, and already completed a 57-story tower in 19 days before most people in the Western construction industry had heard the company's name. But for every developer, every structural engineer, every building code regulator, every cement company executive, and every government trying to figure out how to build more housing for less money and less carbon, who watched that Changsha time-lapse and felt the uncomfortable sensation of realizing that the constraint they thought was permanent might not be. The housing shortage in the United States is estimated at roughly 4 million units. In the United Kingdom, it runs to somewhere between 4.5 and 5 million. Australia's housing crisis has been described by its own Reserve Bank as structurally persistent and not solvable within conventional building timelines. The cities of the global south, Lagos, Nairobi, Dhaka, Karachi, Jakarta, are urbanizing at speeds that conventional construction cannot physically match, even before accounting for the labor shortages and material costs that make the math increasingly difficult in developed markets. Every one of those contexts is a market for exactly what China has built, and the export data suggests that the market already knows it, even if the policy and regulatory frameworks in most countries haven't yet caught up with what their own housing needs actually require. Here is what I want to leave you with, because I think it's the most honest framing of what this moment actually represents. The 10-story building in 28 hours is not primarily a story about speed. Speed is the most visually dramatic feature of it, but speed is a symptom rather than the substance. The substance is a manufacturing philosophy. The idea that the way to solve the fundamental problems of the construction industry is not to make on-site concrete work incrementally faster and slightly greener, but to move the problem into the factory where precision, repeatability, waste elimination, and quality control are genuinely achievable, and make the on-site operation the last, simplest step rather than the main event. That philosophy, applied at the scale and with the industrial policy support that China is now applying it, is not going to be easy for any other country or any other company to replicate quickly. The B-core manufacturing process, the module assembly system, the logistics network, the factory capacity. All of it was built over 15 years of sustained investment that most Western construction companies have not made and most Western governments have not supported. The question is not whether the technology is real. It is. The question is how long it takes the rest of the world to decide whether to build the same capability domestically, buy it from China, or keep arguing about whether concrete with 40% less cement is really going to change anything while the export growth numbers compound at 45% a year, and a woman in Perth realizes she can have a 70 square meter home installed in her backyard for $12,000, fully fitted, before the local builder's quote has even been finalized. Tell me in the comments whether you think modular prefabricated construction can actually solve the housing crisis in a market you know. Well, because the gap between what this technology can theoretically do and what the regulatory environment actually allows it to do is the most important variable in the entire equation, and it's different in every country. And if you want to keep following where this goes next, the licensing deals, the building code battles, the cement company responses, and the export data that will tell us whether 45% annual growth is a moment or a trend, subscribe, because this story is just getting started.